Okay, hello everyone. I want to give this question a go. So this is coming from your mechanics paper. It is let me just get the code. So this is the 2021 paper, zone 42, and we're going to be looking only at question 7 today. So this is quite a mission of a question. I want to encourage you that it is possible and you have everything that you need to do it, but it is a lot of work. I think that's the best way to put it. All right, so I'm going to just try and draw the concepts as I go, and let's see if we can figure out what we're doing here. So you have particle P and Q. They've got a mass of m and 2m, respectively. They are initially held at rest, and they are 6.4 meters apart on the same line of greatest slope, and it is a rough inclined plane. Okay. It's angled at alpha, and then they've given us sine alpha is equal to 0.8. Particle P is released from rest. Okay, so that's released from rest. It lines down the line of greatest slope, and then Q is projected up the slope at 10 meters per second. The coefficient of friction between the particles and the slope is 0.6. Okay. Show that the acceleration of Q up the plane is minus 11.6. Okay, so first of all, we're just doing one thing at a time. Let's take a look at Q. Q, the forces acting on Q as it goes up the plane. We know that it is moving up, so I'm going to take my direction of motion to be positive. Okay. The forces acting on it is friction. So friction is going against the direction of motion. And then we also know that there is a component, mg sine alpha. The weight component is pulling it down. Okay, there's nothing pushing it up, although it was projected. There's no longer a force that's pushing it up. So Q is definitely going to be decelerating. And here we can see that we need to prove a negative acceleration. Okay, so if I look at Newton's second law, the sum of my forces is mass times acceleration. Okay, so I'm still going to use up the slope as positive. So I just like to define the direction that my particle is moving as positive. Otherwise, these questions can get quite confusing. So I'm going to say friction is negative, minus friction minus your weight component is equal to mass times acceleration. Now, you don't want to use acceleration in this part of the question. We have to prove it. Okay, friction is mu times r. And then in this case, we've got our mass of 2m. Our gravity is 10, and our sine alpha is 0.8. And that is 2m, and we don't know our acceleration yet. Okay, we do know our mu for our friction. They gave us that is 0.6. Okay, and then in this case, our r value, so we know that r is going to be acting up. And the only thing acting down is the component of your weight. So if you have weight going down, we know this is 2mg. So my mass component is acting down. Then I know, let me just draw this a little bit longer. That's acting down. I know that I've got weight component going down my x-axis, and I've got my weight component going down my y-axis. And that is going to be my 2mg, which is 10, and then we're going to say cos of alpha. Okay, I haven't really simplified too much yet. I'm going to use my next line to simplify. Okay, so I've got 0.6 minus 0.6 times 2 times 10 is minus 12m cos of alpha. And then here I've got 20 times 0.8, it's minus 16m. Okay, what you will see is you've got an m in each of these terms. So your m can cancel out. The only reason we can just cancel out a variable like this is because we know that our mass is not equal to 0. Okay, so it's not the best math in the world. The only reason you can cancel out terms like that is because you know that mass is not equal to 0. If mass was equal to 0, then we would need to factorize in order to find this answer. Okay, I'm going to look at my cos alpha. So what is my value of cos alpha? So that is also something I'm going to just do on the side. I know that sine alpha is equal to 0.8. And so that means alpha is equal to the inverse of sine, 0.8. And so if I'm looking for cos alpha, put that over there, I'm going to say cos of the inverse of sine of 0.8. Okay, so it's just normal cos and then inverse of sine, 0.8, and that gives me 3/5. So it's good to have an exact value for alpha, or for cos alpha. If we get that in decimals, it would be equal to 0.6. Okay, so it's minus 12 times 0.6 minus 16 is equal to 2a. And if we just simplify this, our a is then negative 11.6. Okay, and that is the answer that we were wanting to get to, so we know that that is correct. Okay, so if they say prove that the acceleration is something, you don't want to use it. You want your final answer to be that that's what the acceleration is. Okay, now let's jump into our second question. Find the time for which the particles are in motion before they collide. Okay, so we know that P is coming down the slope and Q is going up the slope. Now, the tricky part of this question is we don't know if they are going to collide while Q is going up. Okay, so they collide somewhere as Q goes up, or it is possible that as P is coming down, Q is going to go up and down, and they're actually going to collide somewhere a little bit further down. Okay, I would say that's the trickiest part of this question. If you didn't pick that up, you might not realize exactly, you might not get the full marks for this question. So let's just keep our heads about us, bearing that in mind. Those are the two scenarios that could happen. All right, so let's figure out how far Q travels on its way up. So I'm going to just take a look. I'm just going to kind of try and figure out what's going on in my sum here. I'm going to say this is going to go up and eventually it's going to turn around. And so if I do suvat up this arrow, I know I've got my u is, sorry, that's 10 meters per second. My v is 0 meters per second. And I know what my acceleration is, minus 11.6. So I can work out how far does this thing travel until it turns around. Okay, so I'm going to use my v squared is u squared plus 2as. And I might want to just write labels for myself. Max distance, or let's just say max s, that q goes up. Okay, so it might collide before this, but let's just check it out. Okay, so my velocity is going to be 0, my initial speed is 10, my acceleration is minus 11.6, and we want to work out how far does this thing travel. So if I just plug in my displacement, I've got 10 squared is 100, divided by 2 times 11.6. And that is going to be 4.31 meters. Okay, so it's going up for 4.31 meters. I could also work out the time that it takes to go up that far. So I'm just going to use v equals u plus at. The reason I'm doing all of this is because I don't actually know what's happening in this question, and I'm just trying to figure it all out. Okay, so it takes, how long does it take to travel up? That's going to be 10 divided by 11.6. Okay, 0.862 seconds. Now, how far does P travel down? I guess we could say in the same amount of time, because if the one is going up, the other one is coming down. So how far has P gone down in that time? And would they have collided or not? So P moved down in the time of 0.862 seconds. Okay, so let's just grab another color here. If I take purple, I know that my starting speed is naught. I don't know what my displacement is. I now know that my time is 0.862 going down. And what is my acceleration of P? Okay, I might need to quickly work out my acceleration of P. I can do that in the same way that I did for U. So let's just take particle P. The forces acting on P is we've got friction acting up and we've got mg sine theta acting down. Okay, and this has a mass of m. So my sum of my forces is mass times acceleration. I've got minus friction going up plus mg sine theta going down, and that's mass times acceleration. My sine theta, we already know, sorry, not sine theta, it should be sine alpha, is 0.8. And we've got an M and an A. And then here, we already worked out in our previous question, we know that this is mg cos, and so basically that's 0.6, we've already worked it out, plus mg times 0.8. Okay, and this is going to give us, once again, we've got an m in each of our equations. The only reason we can cancel them out is because m is not equal to 0. I would actually write that on my paper because otherwise the maths is questionable. Let's just put it that way. Okay, so now I've got 6. I'm going to multiply that by 10, so 6. My mu is 0.6, I believe. 6. Oh, let me just write this all out. So minus 0.6 times 10 times 0.6 plus 10 times 0.8. And that's my acceleration. So what does this give us? Times 10 times 0.6. And my acceleration of my particle going down is 4.4 meters per second squared. Okay, so P is moving down at 4.4 meters per second squared. Wow, they don't give you lots of space to do this. So, okay, let's just see. My U is naught. We don't know my S, my T, and my A, so I'm going to be using S is equal to UT plus a half AT squared. So I am going, that falls away, a half times 4.4, and then my time was 0.862. Okay, so 0.862 squared times 4.4 divided by 2, and that gives me a distance of 1.634 meters. Okay, so particle P has moved down 1.634 meters. Okay, so this is 1.634, and particle Q has moved up 4.31 meters. Okay, so 1.634 plus 4.31, that gives us a total of 5.944. 5.944. Okay, so they have actually not yet collided, but they are closer together now. My distance between them, so what I'm going to do is I'm just going to take 6.4 and I'm going to subtract the total distance that they went, they are now about 0.455 meters apart from each other. Okay, so they have not yet collided. Now Q is going to turn around and go down. P is still going to continue going down. Okay, if we just take a look at each of these particles, so for P, I know, okay, I don't actually have my starting speed yet. So let's maybe quickly get my starting speed for V. So that's another, I'm basically using all of these variables up here at the top. I'm still going down my purple arrow, so V is equal to U plus AT. So that's going to be my 0 plus 4.4 is what we worked out at 0.862. 4.4 times 0.862. That is going to give me a final velocity of 3.79. Okay, so that is the velocity at this point. So 3.79. It's kind of my starting velocity now when I'm going to do my next formula. So 3.79. Okay, so my U is 3.79. Now I'm going to say that P is going to travel. If I say Q travels X, then P is going to travel X plus 0.455. Okay, so my displacement is going to be X plus 0.455. My acceleration is still 4.4. And my time, the time for both of these to collide is going to be the same. So I'm just going to label it as T. So if I was to write up a formula here, S is equal to UT plus a half AT squared. And that is going to be X plus 0.455 is 3.79 T plus a half times 4.4 times T squared. Okay, so now that's my formula for P going down. If I look at Q, I think one would probably need to use a bit of additional paper on this question. I would be interested if any of you have, a quicker way to do this. I think it would be really helpful just to share it. I'm going to look quickly at Q. So we now know that Q is starting off with a speed of 0. The acceleration of Q now changes. Why is that? Q was going up the slope and now it's going down the slope. Because there is friction on the slope, friction now changes direction. Okay, and mg sine theta is going down. So initially when it was going up the slope, our friction was acting downwards. Now that it's going down the slope, our friction acts upward, and that changes the acceleration of Q. All right, so if we calculate the acceleration of Q, you'll actually see that it comes out to the same thing as P. Because instead of using m, we're now using 2m. And when we worked out the acceleration of P, we crossed out all of our m's. Okay, so that might be something just to take a note of. If you have a slope and a particle moves up and down, if the slope is rough, the acceleration is going to change when it goes up versus when it goes down. If it's a smooth slope, it doesn't change because the only thing that's changing is the friction. So that's one of the first things that I would take note of. And the other thing is that the mass doesn't really make a difference, okay? Providing that there's no other forces acting on this thing. So now we know our acceleration is going down. I'm just going to define the displacement as x, and then my time is also going to be the same time as for particle P. So if I write that up, I've got S is UT plus a half AT squared. So I've got x is a half 4.4 T squared. Okay. What I'm going to do now is I'm going to put my x into this formula up here. So half times 4.4 T squared and T plus, And then it's interesting because on this side, I've also got a half 4.4 t squared. And these entire terms can cancel out because they are the same. And so we find that these particles collide. So if I say 0.455 divided by 3.79, then my answer is 0.12005, okay, seconds. And so if I look at the total time, they want to know, find the time for which particles are in motion before they collide. Okay, so they, first of all, traveled down by 0.862, and then later, so 0.862 plus 0.12, and that gives me a full time of 0.982 seconds. Okay, so if you have a faster way of doing this, I might even sit around and think how to do this a little bit better. If you have a faster way, please do make a comment or something. It'll be really good to hear different people's inputs. I am quite surprised by the little space that they give us to do this question. So it makes me wonder if there is a quick way to do it. Okay, but okay, so one of the other tricks in this question is that we didn't know now, do they collide on the way up or on the way down? And if you get a question like this in exams, I might not start with the assumption that they collide on the way up, but actually calculate and check to see. Okay, and then the other takeaway from this question is that remember, if a plane is rough, the particle moving up is going to have a different acceleration as to when it's moving down. Then last tip for this question is it's just a lot of hard work. So keep going, don't give up, keep going and see if you can actually get to the correct answers. All right, now I'm going to take a look. They say the particles coalesce on impact. Okay, so we are now jumping into our topic of momentum. So finally, these particles catch up with each other and they coalesce on impact. Find the speed of a combined particle immediately after the impact. Okay, so these things have finally caught up with each other, and that was after their time of 1.2. So we're now looking at our second equations. I'm not going to go back to the first ones. We can work, what do we need for momentum? We need the mass of each particle and we need the speed of each particle. So I'm going to go back into my two equations up here. So for P, this is the information that I had. And now I want to calculate my V. And then for Q, this is kind of the information that I had. And I also want to calculate my final velocity. So I'm just going to go back to P. I know that I had a starting speed of 3.79. My distance, so we didn't actually work out x. I wonder if we could get away with not doing that though. Acceleration was 4.4. I don't know my final velocity, but I do know my t was 0.12. Okay, there is a formula for this. V is equal to u plus at. You always need to just know three unknowns, and then the rest you can sort of figure out. So I'm not even going to look at the distance now. So 3.79 plus 4.4 times 0.2, and that gives us a final velocity of 4.318 meters per second. So this is particle P, just before the collision. Okay, and then if we go to particle Q, we also had U is equal to 0. Our acceleration is also 4.4. Our time is also 0.12, so I can work out ID. So 4.4 that is going to give me 0.528. So that's my velocity of Q just before the collision. Right, so if I look at my momentum equation, I know my conservation of momentum formula. Right, so my particle P was M. That's M. And my initial speed was 4.318. And then 2M times 0.528. Here they coalesced, so that becomes a 3M. And we are trying to find out what's the final velocity of these particles. Okay, so once again, I can divide through by M, only because I know M does not equal 0. Okay, then I'm just going to do this on my calculator. So 4.318 plus 2 times 0.528. And then we're dividing everything by 3. That's going to give me a speed of 1.79. And that is the speed of our combined particles. Okay, I hope that was really helpful. Definitely a lot of work going into this question, so let me know if you can figure out an easier method. That's my challenge for you.